type, it says the following. If I have roll f from A to B, for all is the pi type, for all G from B to C, for all H from C to D, then I can prove that if I do first H and then G and then F, and I put the parentheses like these should be equal, and this is propositional equality now. If I first compose H and G, and then I do F. Okay? Okay. I messed up something. What is wrong? Probably using parentheses. Like this. Let's just try. No? Rock experts, what am I doing wrong?
The definition of comp is backwards.
Yeah, are you 100% sure about right associates?
Sorry, first what was wrong in the code? The comp was what? Ah. No?
In the notation.
Ah, the notation was the problem. Thank you. Question about right associativity?
From memorizing the invisible standard library, it's nice to see it right. It's actually level 40 left.
Okay.
But maybe it's different. Oh, I see, because you're redefining it. That's probably why.
It's okay. Like the standard library has its composition, and it's probably the way it is because it's the correct way. But for the purposes of this example, I think this is not fine. Are you understanding what it is? Does somebody have a problem reading it? No. Okay. Betten?
How did you get the circle?
Yes. This is the Unicode LaTeX extension.
I just Googled it.
Or that. But I really love it because I can then write all of the LaTeX in the editor. Okay. Proof. The extensions, I need space. So how do we prove this, right? We do intros for everything. F, G, H. Like this. And now I have to prove this. How do I prove this? It's an equality type. Refl, okay? Reflexivity. Bam! It did it, okay? Now, how would I do it the pedestrian way? How would I do it if Rock wasn't as smart, right? What would be the first, what can I even do here? Yes?
Unfold composition.
Unfold composition, yes. Unfold. Will that work? I have no idea.
Maybe if you put it in quotes.
Maybe, yeah. So I don't, yeah, it works. Yes. Now what? Yes?
Now it's the literal same thing on both sides.
Yes. Now it's reflexivity. Okay. But actually, right, what happens here, yes, we can unfold it. But also what happens is, if you look at this step here before I unfolded it, actually what it does, it uses the eta rule, right? It wants to introduce the x on both sides. So when are two functions equal? When they're equal point-wise. And this is done by rewriting on the left side and on the right side with the eta rule, right? Actually on both sides. And then you can, compute and normalize. So actually what happens is it either, just unfolds all of these and use the computation rules, but also, because these are functions, it has to use the eta rule in the background, right? It's not enough to just use the computation rule for the function, because this is equality between two functions. So to prove equality between two functions, you have to use either the extensionality rule, which says two functions are equal when they're pointwise equal, or you have to, while you're computing away the left-hand side and the right-hand side, this unfold is kind of tricky because it doesn't just unfold one step. It unfolds and then simplifies, right? And the simplification also uses the eta rule. But actually, if you look at this carefully, you can see that you have to use the eta rule or the extensionality rule to prove this equality. So Rock is really smart, right? Eta rules come into play. You just don't see them because, when you say unfold or you say reflexivity, things are simplified. Okay. Defined. Question? No. Good. What did I want to show you next? Let's see, both beta and eta rules have to be used. Natural numbers are just, defined inductively. So what Rock can do, they have a syntax on how to just define an inductive type without specifying the induction principle yourself, right? So what you do is you define an inductive type by, saying inductive, and then you name the type, and then this is, well, it should say type here for the purposes of this lecture, and then you give it the constructors, which are 0, and the successor they call it big S, right? So this is the successor function. So natural numbers are just there, and you can use them, and they're kind of defined the way we define them. So the induction principle, right, is also there. I think it's called not int. Yeah. So we have the induction principle here as well. It's called not int. And we can use it. Okay, so let's try to use the induction principle. So let's say I want to define plus, right? Let's say I want to define plus in a foolish way. Okay. And it will be foolish. It will be something that goes from natural numbers to natural numbers to natural numbers. And then I want to introduce two variables, x and y. And then I want to define the plus function with, actually, I just want to introduce one. And then I want to define a plus function with destruct. So the induction principle. And the first one is that I want to do in the case 0 will be just the identity function. Identity function at. Identity 2. No? Ah, I didn't say that, yes. Thank you. And the second one, so I'm doing now induction on the first argument, but so be it. And the other one would be exact plus foolish of successor of what am I defining? Yeah. Successor of no, it's successor of plus foolish of x, right? Am I missing parentheses? Okay. And then it says the variable plus foolish was not found in the current environment. And this is because if I have a specific recursive thing, I have to use fixed point here instead of a definition. Okay? Fixed point needs at least one parameter. Good. And that. So I'm purposely doing this the pedestrian way so that you go through all of the phases of why is it complaining. Okay? So far so good. Because because I have this, I could just destruct on n. And then this one should be n. And what's the error message now? Type error. I cannot have the, let's do it the smarter way. Let's do it the way we did it in the lectures. And then I'm doing it now on the induction of the second argument. Will that be a problem? Yes, it will be a problem. And then here I need a natural number, which will just be x. And here I need a successor of plus foolish and x. Yes, okay. Okay. I didn't really need the induction hypothesis here, right? So I could just use the struct. Okay? If you need the induction hypothesis, you have to write here induction. Okay? So this one was not so foolish at all. What was the, I'm just trying to figure out the example that I wanted to show you where there's a difference between destruct and induction. I wanted to show you the right units for the 0. Okay. Definition. Oh, I'm out of time already? No, okay, I have 5 minutes, but 0 right unit, which says that for any natural number, for all n, that, comma, n plus 0, that is the right unit, yeah, n plus 0 equals n, okay? I'm not using the plus which is defined because it's already defined. Interest n. And I want to prove that n plus 0 equals n. Okay? How do I do this? Induction. Okay. Let's try reflexivity first, just to see. Okay, it doesn't work. Why doesn't it work? Because now we defined it with induction on the first argument. Okay, so if it said 0 plus n, it works. Okay, because it's just degenerate equality. If I say n plus 0, it doesn't work. So I need induction. It's not a differential equality. Induction on n. Good. And now I have the first argument, the first goal is going to be, the first goal is going to be provide me a proof that 0 plus 0 equals 0. And now the first argument is 0, so I can use judgmental equality, so I can just say reflexivity, and we're done. And in the second argument, for the second step, I need the induction hypothesis, right? So I need to do the induction hypothesis, so I can say simple and use all of my sweet judgmental equalities to simplify this. And now I can do what?
Rewrite.
I can do rewrite, yes. Or how would I prove this? How would I prove this goal in Martin-Luther theory?
Induction, like you know that it holds for the smaller one?
Yes, I do. Here I have IHN. That is a proof of n plus 0 equals n.
Exact IHN? Or use IHN somehow?
Yes, I want to use IHN, and this is the guy.
You do app, like,
The AppSuck. Okay? The AppSuck. I will use the AppSuck. I will use AppS, and the app, the actual of that is called F equal. So I will say print F equal, so that we see what it is. And here it says F equal is blah 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 blah. Okay, maybe I'll just check F equal so that I just see the type, so that I see how to apply it. So it's for all A, B type, I have F, and then I have X and Y, and then X equals Y, F of X equals F of Y. So X equals Y will be my IHN, F of X equals F of Y will be the goal that I want to land in. So really we can use F equal. Now with what function? The function will be F, so I can use exact. Let's see if I manage this in the first try, I'll be very impressed by myself. Okay, F equal, then I have the types are net, and then F is S, and then IHN. Good, it didn't go the way I wanted. The term not has type set. Well, it is expected to have type something to something. Maybe one not too much. No? Is that? It would be this argument. Perfect. So this is the action on paths with the function successor on the induction hypothesis. Okay? And then we have defined. Okay. We could do other tactics like rewrite and so on and so on. So probably the one that you would really want is the rewrite anyway. Let's see what I do here. We could just do injection again. That would also work. So, but this is, I think, nicer. Okay. How many things do I have that I still want to tell you? Not that many. Okay, I have variable conversion, the true and the false, and the element conversion, and then we get into the universes. So I think after we switched up the schedule today a little bit, so you have me twice today. You poor things, you're gonna suffer. Okay, so I would like to put a pause now to this because we have a coffee break, but just, to stay tuned, I want to show you, so what else did I want to show you? I wanted to show you how we can see true and false. I wanted to show you how to do the ex-falso, so the induction principle on the empty type, and how you can see variable conversions explicitly. And then I'm going to do universes, because if I want to do properly the sigma types, it's really nice that you know what's the difference between the special kind of universe the calculus of inductive constructions has. It's called prop, and the rest of the universes that are similar to calculus of inductive constructions and LTT. So we will define the universes first, and then I will show you, how it's a little bit special in Rock. But so what I think is the correct way to do things, and what Rock developers think is the correct way to do things, which might differ slightly. Okay, any more questions about this? Yes.
So, what is the difference putting the total end of that to the left of the colon and to the right of the colon?
Right. That's an excellent question. So I will give you a very specific reason, right? So if you put it on the left of the colon, it's kind of, it's called like a parameter, I think, right? And if it's on the right of the colon, it's like an explicit function, okay? Morally, they are the same, okay? Implementationally, they are not exactly the same. And you saw it when I tried, when I filled it with a fixed point, and then I moved one of the arguments to the right-hand side. So this is one difference with the marginal type theory. So here when I have fixed points, I have to explicitly say, because I said defined here is also a termination checker. And the way it checks so that's a good question. Let me just print plus, okay? So if I print plus here, if you see what it looks like, so the type is correct from not to not to not. But the actual definition is a match statement, so an eliminator, that's okay. But here, something in the curly braces that says struct n, okay? And this is rough syntax for telling you, n here is the structure that is going to get smaller with every call, okay? And when you have a termination checker, you want to make sure that something gets structurally smaller with a recursive call so that you know after finitely many steps it will terminate. And because we want to tell Rob, we want to tell it which thing is the one that's smaller, we have more parameters there, and then we can explicitly say, so sometimes if it's not just one argument that is getting smaller, but it's a more complex thing, you can write a more complex thing like what in this curly parentheses saying, okay, this complex thing is going to get smaller, this complex term is going to get smaller with every recursive call. So it's like a justification that it terminates. Okay? So implementationally, because Rock has this feature, it treats parameters slightly differently from the just normal functions. But like morally, right, it's not a problem. So morally, when you look at what it means type theoretically, the way we presented the rules is the same thing. Okay. Coffee break and see you in the afternoon.
Okay, a couple of things. If you left a mouse in here last night or yesterday, I have it.